Okay, so Kevin, thank you for joining us. So I have three questions which I hope to go through with you, and then maybe we take something from the audience. If you guys have the idea, you should have, because now you've got like lunch and all of that, and we've already went through one session, so you probably have the idea. Okay, so we have three topics: accelerating AI inference, which would have been the title of the thingy. Embracing open ecosystems, a very interesting one, and obviously sovereign clouds and data sovereignty. So my first question would have been, Kevin, with the increasing demand for real-time AI processing, right, which is complex, what are the key infrastructure innovations that your company is implementing to reduce time to inference at scale? And then if you can give examples and maybe a couple of numbers so that we have like a perspective on the scale.
So first, it's great to be here. Excited to meet all of you. And I think this is the right time to have this conversation. A lot of what we've been talking about so far in the various different sessions is how do we accommodate higher densities within the data center given the roadmaps that we're seeing from NVIDIA for new GPUs. And at the end of the day, we're always going to have a model where we need to build supercompute clusters at very large scale to build large frontier models. We're going to need those supercompute clusters in individual nation states so that individual nations like the Denmark here can give that compute capacity to universities, to research institutions, to local startups, so they have access to infrastructure to build native models and to build new services. However, that being said, the long-term trend is that we are not going to go back to a model where we live in the 1960s and we have an MIS department managing a mainframe and everyone is scheduling time on the mainframe to get their punch cards in to do their compute. We live in a day and age of a distributed compute architecture at the application level, and so too will we live in that model going forward on the infrastructure layer. When you look at enterprises today, enterprises are looking to move forward with new agentic AI initiatives. And those initiatives are not going to be centralized in one data center location to serve a worldwide customer and employee community. Those agentic AI initiatives are going to be operating in region and ultimately all the way out to the edge. And so what we do here at Vultr is we do something decidedly different, which is we provision the large-scale training supercompute clusters, particularly as part of our Sovereign Cloud offering. And we also provide the distributed compute infrastructure across 32 data center regions across all 6 continents, so that when you're actually building and deploying an agentic AI solution, you can actually scale globally. You can reach 90% of the world's population or 90% of your employee population in between 2 and 40 milliseconds. That really, truly does matter. So in this day and age of GPU scarcity, it's less the scarcity we would argue in one location. It's more about where are the GPUs to support your operations in Latin America? Where are the GPUs to support your operations in India? Where are the GPUs to support your operations in all regions of the globe that you operate? So that's the first problem with inference at scale, is we need to solve this mindset problem of just worrying about the training cluster. We have to worry about the regional clusters where we tune. We have to worry about the inference clusters that need to be pushed all the way to the edge. That's one thing we do different. The other thing that we do different is, at the end of the day, what's going to power all of your inference, it's going to be data. It's going to be real-time data. And we worry so much about getting data to our training clusters and optimizing the storage array to support high-speed throughput from DDN to the supercomputer. But at the end of the day, this is a distributed application, and there's data that's being collected in individual countries from local devices that needs to stream into a regional cluster to tune a model and also stream real time to a vector database. So for your RAG-enabled application, your employees and your customers have access to real-time data feeds. So there's a whole set of infrastructure that's needed to enable that. First, you need to be able to have the infrastructure in region to handle localized data sets. If you're collecting data from patients in an MRI scan in London, you cannot take that MRI scan and you cannot actually send it to a training cluster in North America. The training cluster, the RAG application, it has to be located in the UK. You also can't send that data over the public internet. You need to have a direct pipe between that local data center where the data is being captured and the GPU cluster where you might be tuning a model. So you need to have the direct connect. It cannot go over the public internet. It is too sensitive. It is too confidential at the end of the day. And then you also need to be able to support the real-time streaming, because it's not just getting it to the GPU cluster to upgrade a training set, but it also needs to be made available to an application experience so that the user can go on their mobile phone, and after they get the email alert that their MRI results have come in, they can open their mobile app and then they can talk to the agent and say, please tell me what I need to know about my MRI, and the agent has to respond. So what we do very differently here at Vultr is all of the above, which is first and foremost, data residency, data privacy, mission number one. Any data collected in region doesn't leave the region. We don't touch it. It's safe and secure. Second, it has to be the direct pipe. So we're going to connect over 900 data centers all around the planet to our GPUs. A dedicated pipe, safe, secure. Nothing's going on. We actually go so far as do it with 5G connections as well. So if you want real ultra security and you have some sensor or device in the field, we'll also connect to via 5G real-time streaming data. And then the second thing is we implement the entire RAG pipeline so that the MRI data that might be optimizing and tuning an existing model can also feed real-time into your vector database, so you can query it and then get that new context to send to the back-end healthcare agent that can then interpret it and then give you a meaningful response. So inference scaling looks super different than anything that we've been talking about in terms of training. Inference actually looks more like traditional cloud-native engineering, and a lot of the principles that we do for DevSecOps pipelines and application architecture and infrastructure deployment using things like Terraform, those all need to get implemented on the GPU side. It's actually new, but it's not new, I would argue. So that's what we like to do. We like to take an approach where we take the best of cloud native engineering principles and then we bring them forward to this world of AI, because why is a GPU that special? Why can't you just turn it on and turn it off like an ephemeral resource like you would like a compute instance? I asked that question. Why is it that special? Should it be? Should it be that hard?
Should it be?
Or should it just be a utility, on, off, everywhere?
You mentioned when we were chatting the idea of openness and open protocols.
Yes.
I was positively almost taken aback because I'm coming from a computer science background with open source software, open education, and all of that stuff.
Yes.
So can you touch upon that before we?
Well, again, I think one of the risks that we run in the GPU world is hyper concentration of capital, hyper concentration of inventory, and worsening a digital divide. And our mission at Vultr is to democratize access to GPUs and first-class cloud compute infrastructure everywhere developers live and work. We should be indifferent whether the developer lives in Johannesburg or Mumbai or Stockholm or Copenhagen. They should have access to the same resource. We should be fully democratizing it. And I think the challenge that we see is, are we building another monolithic closed stack in the AI world, starting from the GPU all the way up through the software stack.
Right.
And I would say if we go that route, we'll wind up with ever more concentration and we will have poor societal outcomes. So what we are all about here at Vultr is open source and open communities and what we call an open composable infrastructure stack for AI. Composability means everything is, atomic, everything is modular, everything is, discoverable and orchestratable. You can basically plug and play it like Legos. I mean, we're in Denmark, it's like Legos. Come on, it shouldn't be that hard. That's why we support top-of-the-line NVIDIA's GPUs from both NVIDIA and AMD. That's why we support top-of-the-line CPUs from Intel and AMD. That's why we have over 200 partners, so you can plug and play different storage vendors. We provide storage services, but if you don't like ours, plug and play someone else's. That's why we have our own direct connects. Or if you don't like ours, plug and play Megaport, plug and play Console Connect. It's all about that composability. There was the talk earlier about is Europe behind and does it need to leapfrog with like quantum? And I'd also challenge all of you. What does Europe always lead in? It's actually really simple. Community-led development. Where would enterprise infrastructure be in the software stack if it wasn't for Europe? If it wasn't for Europe driving open source and open standards. Europe had a scarcity of capital. Europe had fragmented markets when the web came around. I was there. What did Europe do? Did Europe say, no, we're going to be behind? No. Europe basically built all of the infrastructure that 70% of our application code actually relies on. Just look at the Apache Software Foundation for crying out loud, right? So I think there's a real opportunity for Europe to continue to lead, but maybe in an unsuspecting way, but yet very familiar way, which is leverage the power of the diversity of the European Union and leverage the power of the community-led model and invent an open source, open standard stack on top of GPU infrastructure so we don't wind up with a closed monolith world. We feel very passionate about this here at Vultr. Very passionate.
Thank you. We can see that. We have 2 more minutes. I would encourage at least one question. Yeah? Want to go for it? Thank you. That was good. Thank you.
Yeah.
Thank you. I'm just wondering, could you perhaps share what kind of use cases you're seeing for this like ultra low latency inferencing? Because ultimately it feels like you should really care about times to the first token, and it doesn't really matter if it's like 5 milliseconds or 50 milliseconds, if you're still limited in terms of the throughput. But yeah, it'll be great to hear more about what you have in mind.
Yeah, so we can look at 2 use cases, both of which demand immediacy of response. So in the first example, let's just talk about human beings and our own experience. So we've all undergone this whole customer experience revolution. We don't have any tolerance for waiting for a response. We demand immediacy of response. We're trained to not accept low latency, otherwise we swipe, right? And so if you look at, again, the healthcare example, that's a case where I want immediacy of response. The moment I get a notification that my new lab test results are in, I want to open up my Kaiser application and I want to click the button to talk to the agent, and I want to know, is there anything I should be concerned about in my lab test results? And I want the voice to respond in less than 1 second. If the voice takes longer to respond in more than 1 second, I am not happy, and I'm going to call the customer service line. I'm going to try to book an appointment. I'm going to be a super unhappy patient, okay? So, and a lot has to happen to get that sub-second response time, right? Because you're not just, you're hitting the RAG database, you're actually having to fetch the lab results, you're having to send it to the backend LLM, you're actually having to, but first of all, you have to decode my voice to understand what the question is, right? And then ultimately you have to encode that back into a voice and actually get that response. All that has to happen in less than 1 second, because as human beings, we do not tolerate long wait times for things, right? So that case matters. But you can also look at it in terms of an actual agent model. So say, for example, you actually are running a train, and you have to have a drone after a storm actually inspect the tracks, because you want to make sure that there's no heavy debris on the track that's actually going to potentially derail a train when it's going around steep turns. So you have a drone flying overhead, and the drone's actually inspecting the tracks. The drone's doing some real-time inferencing on the edge device, so it's filtering out anything that's not a significant, like a leaf, for example. It's not going to send that data back. But when it notices something that's a fairly large object, like a branch, then it will actually have to stream that thing back. It's going to have to stream it back to a collection of agents, okay? Because there's going to be different agents that are going to have to be involved in, first of all, analyzing the imaging, correlating that image to other types of objects that they know that have been problems in the past. Then another agent has to actually make the determination whether or not it's significant enough to actually fix. Then another agent's going to have to do the scheduling for a repair crew. There's probably a swarm of agents that have to get involved within analyzing that feed. The drone is flying at 150 miles an hour, right? And that drone's going to keep going. So those agents have to pick up and make a decision very, very quickly on what to do, because the drone could be picking up another fallen branch 2 seconds later. So that's another example where the latency, the inferencing has to happen within that swarm of agents has to be blazingly fast, like microseconds, actually. And that's also really critical. That infrastructure also needs to be closer to the edge, because if you're going to round trip that to San Francisco from Finland to get a response, no, you need the inference infrastructure in Helsinki.
Does that answer your question? Oh, you meant something else.
Okay.
Thank you very much.
Well, we'd love to follow up more on that then.
We ran out of time. Ladies and gentlemen, thank you very much. Hope to see you again soon.
Thank you so much.
Thank you, Kevin.
Thank you.